There we go. Okay, so we are going to get started because we once again have a really packed schedule for you all. My name is Ana Aranda. I am the Community Outreach Coordinator for the NASA Scope team. And on the line, we have Kay. As you all know, Kay is the organizer for the Solar System Ambassadors. And we have Vincent. And Vincent is actually joining us from Alaska. So he's going to have a lot of fun Aurora science stuff to share with you all. But really quickly, I'm just going to dive into Scope. So we are a NASA Science Activation team. The community that we serve is the other NASA Science Activation teams, subject matter experts such as yourselves, and early career scientists. And the domain in which we do this practice is the Earth and Space Science and Engineering education. And our practice is to create inspiring educational materials and experiences that are effective, true to science, and are inclusive of all audiences. So that kind of ties into our heliophysics workshops that we are bringing you all. And this is the second one in the series. We have 2 more left. So one next week and the week after. So be on the lookout for some more emails that is going to be coming from either Kay or myself about how to register. So now I'm going to introduce our guest speaker, Vincent. So Vincent is a professional aurora chaser and photographer living in Fairbanks, Alaska. He is a PhD student at the University of Alaska Fairbanks studying space physics. His goal as a photographer, scientist, and altruist is to inspire others through photography to help educate people on the science of auroras and broader concepts of space weather. So I am going to stop sharing, and Vincent, you can take over.
Awesome. Thanks for that introduction. Let's get started. All right, everyone. I'm happy to be here. My name is Vincent Ledvina, and I will be covering, to the best of my ability, the science of the aurora, and also hopefully inspiring you with some cool citizen science initiatives that will teach you how you can help advance our field forward. So, really quickly before I get started, just want to thank NASA Scope and also the Solar System Ambassadors for giving me this opportunity. So the bottom line up front. And this is something that we're doing at Aerospace. So I'm an intern at the Aerospace Corporation, and something that people are pushing is sort of the very beginning of the talk, sort of tell people what your goal is. So what is my purpose here? Well, my purpose is to teach you about aurora science and why it's relevant right now. And I'll be getting into what's going on with the sun. And then I also want to invite you to become citizen scientists, and I'll explain what that means towards the end of this talk. And finally, I really want to inspire you to be a space weather ambassador in your community. So, the sun is really active right now. We've been having a lot of auroras, and this means that we need people who know what the science is and sort of how to translate all of this information down to a sort of general public level. There's a lot of misinformation out there as well, and it's important that people are not fed this misinformation and given false hope, let's say, if there's a big solar storm coming. So that's really my goal by the end of this, is that you're confident enough to go out into your communities and sort of, proselytize the science of space weather and how people can contribute as well. So here's just a little outline. I'll first introduce myself and what the aurora is and sort of why this matters. And then I'll get into the actual science and the meat of the presentation, which is all about what is the aurora, what is actually happening on a scientific level. And then I'll sort of dive into space weather and also the different space weather phenomena and which ones are responsible for creating auroras here on Earth. And then, of course, I'm an aurora chaser. This is what I do in my free time. I don't really sleep that much. So I'll tell you how to see the aurora and give you some really practical tips for that. And then finally, I will talk to you all about citizen science because I'm really passionate about getting aurora chasers involved in doing real research with scientists. So a little bit about me. You already heard a bit of this, but people like to call me the Aurora Guy. I was kind of given this name in North Dakota when I was doing my undergrad studies there. So I would take pictures all the time. And actually, one of them got shared by the University of North Dakota, and it got a bunch of likes. This was sort of before I was on social media and really doing this professionally. I was sort of just, as a hobby, going out and taking photos of the aurora when I could. And I was actually approached at a bar twice in one night by random people that were asking me if I was quote unquote that Aurora guy who took the photo that UND shared. So after that, my friends just started teasing me and calling me the Aurora Guy, and that's where I got the name. So my website's theauroraguy.com, so it's kind of stuck around. But yeah, I've really been inspired throughout my entire life, and from a very young age, to study space weather and go into space science and space physics. So I saw the aurora first time when I was 4 years old in the Twin Cities. I'm from Minnesota, from a little suburb called Maplewood. And I think it was Halloween, so October 31st, 2003, I was trick-or-treating, and on my way home, I saw the aurora when I looked up in the sky, and I was just watching the lights dance right around my house in the middle of the city. So it was a really fantastic experience. And, obviously I didn't pick up a physics textbook the next day. I didn't start grad school when I was 4 years old, but I think that experience of just, connecting with the sky and sort of this, like, I guess at the time, this sort of mysterious and very otherworldly, very unusual phenomenon. I think that embedded this passion for the night sky and learning more about the cosmos in me, which made me pursue space physics when I eventually went to college at UND. So now I'm up in Fairbanks, Alaska. I graduated with my bachelor's in physics in 2022. And while I was at UND, I did a lot of aurora chasing. I became active on social media and started teaching people sort of on my own at my campus and in my astronomy club about space weather. And, over time was just learning more and more about this stuff, and realized how much of an impact it could make on people and their, everyday lives. So moved up to Alaska after taking a gap year. I did a bunch of aurora chasing all over North America. I went to Churchill, went to the Yukon, went to Iceland as well, and of course Fairbanks. So I've seen the aurora hundreds of times. Right now, I'm an intern at the Aerospace Corporation. So I just got back from Los Angeles a couple of days ago. And there I'm doing research for my thesis, which is on auroral beads, and also looking at the ways that spacecraft are affected by the aurora. So in fact, when spacecraft, especially those that are low flying, pass through auroral arcs and also really high energy precipitation from aurora, they can be affected, and they can be negatively affected through like spacecraft charging and also single event upset. So trying to look at better ways to model where these auroras occur, and then also better understanding the impacts on satellites. It's sort of what I'm doing down there. And of course, I'm passionate about citizen science and science communication. The aurora is I think one of the only phenomena in astrophysics, sort of in physics, where you can actually go up and see it with your own eyes and kind of experience the science. I always say the equations are written in the sky, and it's true. I mean, you can see these auroral arcs and these curtains, these shapes in the aurora, and tie that directly back to certain processes, plasma processes going on in outer space. I just think that's really cool. So I'm going to delve right in. So what's going on with the sun? I'm sure all of you are here because auroras have been at the news a lot, right? We're seeing auroras now. It seems like every single week, every other week, in like Michigan or Minnesota, or even further south in the northern hemisphere in like Mexico or southern Arizona, Texas. And really, that's all a function of the solar cycle. So, and I'll touch on this again in this presentation, but the solar cycle is this 11-year activity cycle on the sun where we have like a low season and a high season. So it's not a single point solar maximum or minimum. It's sort of this gradual ramp up and ramp down. And right now we're in the solar maximum phase. And I should have updated this plot because we just, in September, received the monthly sunspot average for August, which was the highest it has been since 2001. So the sun is the most active it has been in over 20 years. And as a result, we're seeing more space weather, and more space weather causing more auroras. And I'm sure a lot of you saw the aurora in May. It was one of the biggest events that we've seen in the modern era. Auroras were spotted as far south as places like Puerto Rico, Hawaii, the Yucatan in Mexico, the Middle East. I even saw the aurora in a very unusual place, and you'll see a photo. You'll see my photo of that later. But the solar cycle is really to thank for all this activity, and what that means for auroras and what space weather is. We'll just cover here. So here are just I just Googled auroras and I clicked on the Google News tab, and course, we've seen tons of displays. California, Texas, you know, Utah, Oregon, Nevada. I mean, you name any state, and it's seen aurora this year. Literally every single state, I think, in the United States has seen aurora at some point in 2024, which is just really cool. Now, it also means that auroras have sort of become quote unquote mainstream. There's this really cool visualization. I don't have it here in my slides, but I'll just mention it. If you go to trends.google.com, it shows the search relevance for any search term, and it's a sort of relative scale. So you can go all the way back to when Google started recording these metrics in, I think, 2005, and you can see basically the popularity of a certain search term over time. So like, you know, if you look up Mariah Carey, for example, right around Christmas every year it spikes. But if you look at auroras, you know, if you go to 2024, early 2024, you'll see it, you know, it's kind of bouncing up and down. You can actually do a cool thing where you correlate that with KP index, which is a measure of geomagnetic activity. But if you move that sort of window to the end of 2024, everything else becomes zero and May is 100. So, you know, the May storm this year was definitely the most popular space weather has gotten in terms of the media and sort of the general public awareness. And, you know, as a result, we've seen, and this has always been an issue, but especially now, we've seen a lot of misinformation about space weather. We've seen some articles come out that are just flat out wrong, a lot of clickbait. I always say that if my mom is texting me about space weather and she's worried, then we've officially sort of lost our way because, you know, there's just tons of misinformation out there and people don't know how to sort through it. So my goal with this talk is sort of to give you the right information that you can then take back to your communities and tell your family, your friends about what space weather really is and also what auroras mean and how they're formed as well. So what is the aurora? Well, the definition depends on who you're asking. And really, you know, you could forget everything in this talk and just take home the message that the aurora is beautiful. That's really why I'm into it. That's really why I'm passionate about it. It's not necessarily the science. It's really just the fact that it is just spectacular to look at. It is the most spectacular light show that nature has to offer. That's how I like to put it. And it's also a piece of identity for many northern cultures. So up here in Alaska, you know, the aurora is something that we experience every single night, more or less. And that's ingrained into the culture of many Native communities up here, as well as other Native communities in northern Canada and across northern regions in the world. So, you know, it's not just this beautiful thing, but it's tied to, you know, deep rooted beliefs and spirituality for many people. If you ask a scientist, it's light emissions caused by charged particles from outer space streaming along magnetic field lines, colliding with gases in our upper atmosphere. So it's kind of a mouthful, and maybe it sounds like a foreign language to you. Hopefully it will be more understandable in 15 or 20 minutes here when I explain everything. But, you know, just to sort of reiterate, it is just this captivating, mysterious, and awe-inspiring phenomenon. And everything's connected to the sun, right? You've probably all heard of space weather, but just like we have weather here on the ground, on Earth, we have clouds, we have rain, and we have wind. We have the same going on in outer space, and it's all caused by the sun. You know, if you look up at the sun, it sort of looks like this, you know, white or yellow ball of light in the sky. It doesn't look very, you know, it just looks very constant. It's always there. We can always rely on it to rise and set. It gives us life on Earth. It gives us heat. But if you sort of look at it in a different way, and I'm going to tell you all about that and how we can actually look at the sun in different wavelengths and see the activity and the dynamics. And if we do that, you know, we can see the sun is a lot more than just this white fuzzy ball in the sky. It's really full of activity, and it's creating these dynamic bursts of energy. There's a solar wind that's flowing out from the sun, which is streaming past all the planets and other things in the solar system and creating weather. So just like we have clouds, wind, and rain on the ground, we have the same thing in outer space. And this space weather eventually hits Earth, and interactions take place and can cause the aurora. So the actual definition of space weather is it refers to conditions around a star like our sun, and it's interplanetary space that may affect space and ground-based assets as well as human life. So as we'll see in a little bit, you know, space weather not only creates the aurora, but it can also have some potentially devastating effects on the daily lives of everyone, including a lot of effects on space and ground-based technologies. So when somebody asks me what space weather is, you know, it's really kind of hard to give them that mouthful, right? You know, conditions around a star like our sun, and blah, blah, blah. But what I do is I just show them the aurora. The auroras are really great. It's just amazing for science because It's the way that we can really relate space weather down to somebody who doesn't know anything about it. I show somebody a picture of this aurora and I say, this is space weather. And they're like, oh, really? I thought it was just, lights reflecting off ice or something. But no, the aurora is a direct product of space weather. It's a direct product of something that starts on the sun and follows the sun-earth line from sun to mud. And we can see that with our eyes. It's a way of us really seeing what is usually invisible here on the ground on Earth. We can really relate and study space weather through the aurora. So it all starts with the sun. I just said some of this, but the sun is made of gas and plasma. I think it's a G2 type star, so it's fairly ordinary in terms of the gamut of stars you'll find in space in our galaxy. It's composed of layers. So starting from the core, where there's basically a constant thermonuclear bomb going off and nuclear fusion taking place. All that energy then radiates out through the sun. There's convection that creates a solar dynamo, gives the sun an intrinsic magnetic field. And then the layer that we see, the actual sort of surface of the sun, is called the photosphere. And that's that image on the right there. And you can see these little black pock marks. That's not dust on your monitor. Those are sunspots. It's kind of like the sun has acne. So those are sort of bundles of magnetic fields that have bubbled up like submarines breaching the surface of water that we then can see with telescopes. And actually, you can actually see these with your own eyes. If you have solar goggles and the sunspots are big enough, you can see sunspots right on the surface of the sun. But the surface of the sun doesn't stop at the photosphere, or rather the atmosphere of the sun, but extends outwards. So we have the corona, which is sort of the outermost layer. Besides that, I think let me make sure I get this right. There's a transition region, and there's also the chromosphere, and then you get the corona. So there's multiple layers as you go higher up, where the sun just gets less and less dense, and that atmosphere sort of fades away. And the corona is what you're seeing here with the total solar eclipse. It's sort of that white bit that streams out from the sun. It's the outermost layer and forms the very beginnings of the solar wind. And the solar wind is sort of like this constant breeze that streams out from the sun. I always, liken it to a cup of coffee and, steam off the top of the cup. The sun is that hot cup of coffee and the steam is a solar wind. And the sun is dynamic. There's events that occur on minutes to hours, timescales, seconds, and there's also the solar cycle, which is every 11 years. So we can see the sun in many different ways. So just want to preface, if you see slides that look like the sun is not what you imagine it, that's just because we're looking at the sun in different wavelengths. So as we go into space, we're able to utilize ultraviolet light, which would usually get absorbed by our atmosphere here on Earth. And we're able to see the sun's magnetic fields and how the plasma interacts there, which can give us insights into solar flare formation, coronal mass ejections, and how they launch off from the sun and things like that. So the sun's energy, goes out through the solar system. The solar wind sort of transports this energy along magnetic field lines that envelop the entire solar system in what's called the interplanetary magnetic field. And these charged particles are streaming along these magnetic field lines out through space. And when these charged particles in the solar wind hit a planet that has a magnetic field and a magnetosphere, interactions can take place where the energy is funneled down over the planet's magnetosphere and also penetrates down into the planet's sort of near space environments, near planetary space environments. And in the case of Earth, we have roughly a dipolar magnetic field like a bar magnet. So these sort of weak points are over Earth's geomagnetic poles. So this protective bubble that is formed around Earth by our own magnetic field is called the magnetosphere. And the aurora is formed by a lot of sort of large scale processes through this energy transformation from the solar wind down into the magnetosphere, but also small scale processes that are more on the scale size of atoms and molecules, and also involve a lot of quantum physics, actually chemistry, things like this. So the aurora and what causes the aurora is fairly complex, but I like to break it down and into these large scale processes and small scale processes. So on the large scales, it's really a function of all this incoming solar wind activity. So this coffee cup steam or of charged particles that's flowing out through outer space eventually hits Earth's magnetosphere. The energy gets directed and sort of funneled over our poles through a process called the Dungy cycle. And if you're wanting to learn more about the Dungy cycle and a lot of these other phenomena, I have a site at the very end which you can visit where I've linked a lot of really helpful articles from the NOAA Space Weather Prediction Center and NASA that sort of delve more into these concepts. But the Dungy cycle is really the mechanism by which flux in the solar wind particles are sort of, I guess, funneled and sort of shifted around Earth's magnetosphere. It's sort of like this entire song and dance that happens. People always say that the sun is like the first chef, throwing, raw eggs at the Earth. Like imagine a chef throwing raw eggs across the room, and then the Earth's magnetosphere takes those eggs and scrambles them up and cooks them, and then we get the aurora as a result. So there's a lot of complex interactions that go on within Earth's magnetosphere. And really the takeaway is that the solar wind, is not directly hitting our atmosphere, but has to be funneled around and sort of processed by Earth's magnetic field. So the energy that's able to penetrate down is what is it, those particles eventually become aurora particles when they're energized by magnetic fields around Earth. So, on a large scale, we get two auroral ovals over the geomagnetic poles. We get the aurora borealis, which is in the northern hemisphere, and the aurora australis, which is in the southern hemisphere. And in these areas, the aurora occurs every day, or rather every night. And so, if you want to plan a trip to see the aurora, which I'll give tips on in a little bit, you want to go underneath those auroral ovals. On the small scales, you have these particles streaming along magnetic field lines over Earth's poles. These charged particles have some sort of energy, so they penetrate down, but eventually they reach a region of the atmosphere that's too thick for them to continue. So depending on the particle's energy, they'll either deposit way up in the atmosphere or lower down. So they can interact with different gases sort of on the way down, which are just naturally found in the ionosphere, the upper layer of Earth's atmosphere. The ionosphere is composed of many layers, which sort of overlap with the thermosphere. But we're talking about altitudes from 100 kilometers to 500 kilometers. So of course, above your normal weather on Earth, and certainly above all clouds. So if you're trying to see the aurora, it needs to be clear out. But the ionosphere is mainly composed of oxygen and nitrogen, but not the stuff that we breathe. We're talking about species that have sort of dissociated as the atmosphere has gotten thinner and less dense. These O2 molecules are able to break up, and different processes that break up these molecules and also recombine them take place and create sort of a charged layer of particles very high up. So collisions occur when these particles from outer space stream down along Earth's magnetic field lines, and these collisions sort of liberate electrons from the outer orbital shells of these ionic species, these oxygen and nitrogen ions. And when these electrons are liberated or bumped up to a sort of higher energy shell, they eventually have to de-excite. And when they de-excite, that energy is then released as a photon in a specific wavelength. So we get green aurora at specifically 557.6 nanometers. We also get red aurora from oxygen at higher altitudes, and we get blues from N2 plus at the same altitude as green. And then below the green, if the particles coming from outer space are very energetic, we can get what's called the nitrogen fringe, which is actually caused by diatomic nitrogen being excited. So what happens when the sun gets angry? Well, like I said, we have auroras all the time underneath the auroral ovals, but these auroral ovals can expand to lower latitudes when there's geomagnetic activity. So there's really three types of space that are relevant for aurora. We have high-speed streams, CMEs, and solar flares. Solar flares and CMEs are related, but technically not the same. I like to say solar flares are like paparazzi flashes, or they're these big bursts of light. Basically, magnetic field lines around active regions on the sun become tangled up, and they have to release that pent-up energy in the form of magnetic reconnection. And when this happens, a bunch of X-rays and gamma rays and really radiation across the entire electromagnetic spectrum is released. So these are measured on an A to X scale based on X-ray intensity, A being the weakest, X being the strongest sort of tier of solar flares. And then very commonly alongside these solar flares, CMEs occur, which is where large chunks of the sun's atmosphere are sort of blown out into outer space. And like cannons, and these cannonballs being the CMEs, the cannon could either be directed at Earth or away from Earth, slightly above, slightly below. So, tracking these CMEs throughout space is a challenge and a job by a lot of space weather offices. And we can use what are called coronagraphs, which is what you're seeing on the right here, which are basically artificial eclipses put in front of the sun with an occulting disk. These can be either ground-based or space-based. The one you're seeing here is the LASCO coronagraph on board the SOHO satellite. So you're able to see these big ejections coming off the sun because we're blocking out the sort of solar disk and all the really bright light from the sun. So actually, this this white circle right here is what the sun would look like. That's about the size of the sun here. So you're seeing these CMEs are huge. I mean, they're, at times multiple solar radii. They're these big clouds, sort of sun sneezes of plasma. So they're made of charged particles. They have their own sort of enclosed magnetic field. And again, they can either be directed or towards or away the Earth or away from the Earth. Solar flares may trigger CMEs, are often related, but CMEs may also just come from filaments. So sort of plasma that's suspended in the sun's atmosphere can become unstable and just lift off spontaneously. And it's important to say that CMEs, not solar flares, cause geomagnetic storms, because a lot of people see a big solar flare and they immediately say, okay, we're going to see aurora, but you might not get a CME with that solar flare. The CME might just have kind of, been fizzled off in a different direction. It might have sort of taken a weird course. It might not even be directed at Earth in that case. So it's really important to drive home the fact that not all flares cause CMEs, and not all CMEs are directed at Earth either. Coronal holes appear as dark patches in extreme ultraviolet light. So again, this is measuring the sun and looking at the sun at a different wavelength that allows us to see the magnetic environment in the sun's atmosphere. So what you're really seeing here is cooler plasma. That's why it's darker, because the magnetic field lines are open. So this cooler plasma and the solar wind then is able to stream out very quickly, and you get sort of this region of high-speed solar wind that rotates with the sun. So you get this down here in the bottom right, you get this shaded region, which is showing you the fast solar wind. It creates a compression region at the front and a sort of rarefaction region at the back. And you get what's called a co-rotating interaction region in front of the coronal hole. And then the high-speed stream follows. And then you get normal solar wind after. And since these coronal holes are fixed on the sun's surface, as the sun rotates roughly once every 27 days, I always like to say that these coronal holes are like lighthouses, right? That's sort of this beam sweeping out throughout the entire solar system of fast wind. So these usually only cause minor geomagnetic storms, but they're relatively easy to predict because you can see these coronal holes on the sun, as soon as they rotate in, and they can last months in some instances. So effects of space weather on society, this could be an entire other hour-long talk, but space weather affects everything from satellites in space to power lines on the ground. There's just so many different effects of space weather. For example, solar flares and the ionizing radiation from solar flares can produce a thin layer of electrons in the D region of the ionosphere, which can hamper sort of over the horizon communications with HF radio that rely on propagation through the ionosphere. So using the ionosphere as sort of a duct for people to be able to communicate over the horizon, because these high frequency signals need to sort of bounce around in the atmosphere so they can eventually find their way back to the ground. So when you have this layer of charged particles that absorb the HF signals as soon as they go up, well, you can't transmit any high frequency signals. So big solar flares and big bursts of radio frequency as well, which can sort of drown out the HF signals as well, can cause a lot of issues for amateur radio operators, but also air traffic control. So there was actually a sort of garden variety X flare in December of last year, which almost shut down airspace over the Pacific Northwest because pilots could not communicate with air traffic control for many minutes. So, space weather, just regular space weather during solar maximum, can be very impactful, and especially on power grids as well, when you have very strong currents in Earth's atmosphere, which can happen with the aurora high up in the atmosphere. Due to basic electrodynamics, you can get an induced current in the ground, which can then travel up through power lines, and especially over long runs of power lines, like you might find in rural communities, and over very conductive ground, like for example in northern Minnesota's Iron Range, one of the most susceptible areas in North America to these geomagnetically induced currents. These currents can damage transformers that are sort of end of life or just about to fail. But if you have a lot of old transformers and you have this sudden stress on the power grid, it can cause cascading failures. So we've seen that before with large solar storms in 2003, and then also in the 1980s. And then again, of course, with the Carrington event in 1859, it was really the telegraphs that were sort of messed up. But space weather can have some pretty serious effects, and I've only touched on a few of them here. On the aurora, these geomagnetic storms cause the auroral ovals to expand. So again, geomagnetic storms are caused by coronal mass ejections and coronal holes. They can also just happen randomly too, but really from these, fast streams of solar wind or these gusts of wind, these solar storms from CMEs. And as you can see here, this is sort of the normal auroral oval centered around geomagnetic 68 degrees roughly, geomagnetic north. So we're only looking at the northern hemisphere here. There's, of course, an auroral oval on the southern hemisphere as well. But during a geomagnetic storm, this auroral oval can expand and then auroras can be seen or further towards the equator. So I said that I was going to show you a weird aurora picture while I was on vacation in India in May, and I actually saw the aurora during that huge event. We had a KP9 or extreme solar storm, which basically created a giant auroral oval that expanded all the way down to very, mid latitudes. And the aurora was so strong that if you're looking from the side, right, you can see the whole extent of the aurora. And yeah, I could see a very faint red glow. So, I mean, obviously this aurora right here is probably, 1,000 kilometers away, but because it's so tall, right, you can see, over the horizon of the Earth, this aurora. So it was really cool. I was not expecting to see the aurora on vacation in India. Can you forecast the aurora? Well, you can, but it's pretty hard. It sort of, boils down to how well can we forecast space weather, which is not very well. People say that we're roughly at a level of confidence with space weather forecasting that we were at with terrestrial weather in the 1970s, meaning that we just don't really know the physics, we don't really know the science, and we don't have the measurements either to understand what's going on. But we can make educated guesses and we can get some semblance of what could be coming. So there's this 27-day forecast, which is what a lot of apps will sort of use. And if you scroll down, you can see, oh, there's a KP 5 or 6 predicted for October 16th, right? Or, something like that. And what they're really relying on is that 27-day rotation period of the sun and those coronal holes. So it's betting on the fact that, okay, we saw a coronal hole make a KP6, yesterday. So in about a month, we should see it rotate back around. That doesn't always work because coronal holes can close up. They don't last forever. Now, 1 to 3 day forecasts are great for coronal mass ejections. That's kind of when those get factored in because the travel time from the sun to the Earth is roughly 1 to 3 days for a CME. And then hours to minutes, you can get some more information, of course, because we have upstream monitors a million miles away at Lagrange point L1 that are sort of parked there to monitor the incoming solar wind that's going to be hitting our planet. So, because it's a million miles away, if you see, a huge CME about, happening at L1, you have roughly 30 minutes to an hour to sort of prepare or sort of get ready for that to actually hit Earth. So we can get measurements like magnetic field, strength, and also the components of the magnetic field, the BX, the BY, and BZ. Remember, we're in 3D space, so we have to worry about vectors and their components. And we can also get solar wind density, and then from that we can drive the speed and also the temperature from those measurements. So beyond solar wind, of course, there's ground magnetometers, there's webcams, there's real reports on the ground, which are really the best way of tracking the aurora because that gives you the ground truth information that is the most helpful. So where to see the aurora? Well, go to the auroral oval. The southern hemisphere auroral oval is kind of hard to get to because we have things like the Southern Ocean and Antarctica that are sort of in the way. So northern latitudes are best. And here's just a smattering of locations that are all good for seeing aurora. These will get auroras every single night. It's dark and clear. And also dark is important to drive home because a lot of people try to plan aurora vacations in June and July in the Arctic, and that's just not going to work because you're going to have midnight sun to deal with. And even in Alaska, if you have a huge event like the May event this year, well, it was almost 24 hours of sunlight here in May, so nobody saw anything. So don't be that person to go to Alaska in July to see the aurora. It's just not going to happen. It's just not possible. So it seems that as well, the spring and fall equinoxes have more activity than the solstices, and scientists don't actually know why this is. It's called the Russell-McFerrin effect, and you can see here the number of substorms. So these are sort of like bursts of aurora that happen every night usually, and they really do peak around March and September, and also the sort of shoulder months as well. So March and April, and then September and October are good for auroras. So if you're planning to come to Alaska, for example, springtime is usually a really good sort of clear period. You want it to be clear as well. You don't want any clouds. So March in Fairbanks is just swarmed with tourists trying to see the aurora. It's by far our most popular month here. So, really getting down into the details, a third quarter or new moon is also nice because that dark sky will give you more contrast in the aurora. Little fun fact is that in the Arctic, the third quarter moon does not rise above the horizon, and the first quarter moon does not set. So keep that in mind when you're planning your trip. So really quick tutorial on how to take a photo. Your smartphone camera can do it automatically. Your DSLR mirrorless camera, you're going to want to throw it into manual mode and choose these settings. I always say 5 to 10 seconds is good because you don't want to blur out the aurora. The aurora can move pretty quickly, and if you have too long of a shutter speed, you're just not going to see anything. It's just going to look like a blob. So these were sourced from my friend Mike. He does aurora tours, and he uses a shutter speed usually from 2 to 5 seconds to get that detail. Especially when the aurora is going through one of these substorm phases, it moves really quickly and can get really, really bright. You don't even need a long shutter speed to actually have a properly exposed image because it's already bright enough. You want to use your lowest f number. So your widest aperture, and this should say ISO 1600 to 6400, although ISO 160 is not too far off. When it's a full moon, it's so bright out that I'll use ISO values at 400, 200 sometimes. So actually, this isn't even that inaccurate, but shoot raw and use a tripod as well. Even with a 5-second shutter speed, it's really hard to hold your camera still for that long. You're definitely going to notice the little blur in the stars. So did you know that your photo that you just took, let's say that you were out taking a photo, can actually be used for science? Well, this is where the citizen science comes in. So citizen science is defined as organized research in which members of the public engage in the processes of scientific investigations by asking questions, collecting data, and or interpreting results. There are some principles of citizen science here, just for the sake of time. I'm not going to be delving into them one by one, but really what this boils down to is that if you're somebody interested in science, there's ways that you can contribute to whatever field you want, whether it's biology, whether it's astronomy, whether it's aurora science, for example, through projects and also directly contributing your data to scientists. And so citizen science looks like all sorts of different things. You have educators interacting with scientists in classrooms. You have people on their phones in forests taking pictures of plants to log them and compare with what other people are seeing. And of course, you have Aurora. You have Aurora citizen science as well. So in terms of Aurora citizen science, Aurora chasers are really pioneering the field of heliophysics. And these are just some recent discoveries by citizen scientists, these strange aurora-like phenomena in some cases, because, for example, the one on the left here, some of you may know what this is not technically an aurora. And that would be Steve, which is a viral, the most viral citizen science story in heliophysics. So just really quickly, the story goes that you had people taking photos of the aurora. They started noticing this white/mauve arc with this weird green picket fence feature right below it, appearing right after substorms during geomagnetic storms, but at lower latitudes. So we're not talking about the aurora oval. We're talking about places like North Dakota, Alberta, in Canada. So sort of in this subaurora region, and they were calling it a proton arc. And then they went to scientists and said, hey, we're seeing this weird proton arc. Look at what we're seeing. Showed in the back of their cameras, and the scientists said, no, that's not a proton arc because you're not supposed to be able to see a proton arc. This is something completely different. So then the citizen scientists said, well, what are we going to name this thing? The scientists are all scratching their heads. So if you've ever seen the movie Over the Hedge, this is where the name Steve comes from. So somebody at NASA said, well, we have to give this thing some sort of legitimate name. So now they're calling it strong thermal emission velocity enhancement. So what this actually is unlike normal aurora, that's particles precipitating down from outer space, hitting gases in the atmosphere and creating very specific wavelengths of light. Steve is actually a very hot flow of plasma in the upper atmosphere that's so hot it's glowing sort of white hot, right? If you heat up a metal rod, it starts glowing like a red or like a white color. It's basically the same thing. It's called a continuum emission. So there's no specific emission lines in the Steve, but rather it's just the entire spectrum is lifted. So using swarm satellite data, Liz McDonald and colleagues found out this sort of hot flow of gas, and thus the study of Steve was born, and it really just sort of upended our entire idea of what's going on and how the magnetosphere and the ionosphere interact. So this really birthed a sort of modern day of aurora citizen science, and that was just a few years ago. And now we have sort of friends of Steve. Steve's family is growing. I think we have Steve's brother, we have Steve's twin, we have all sorts of relatives, if you will, and we also have friends. So we have Rogda, which is red aurora with green diffuse arc. Scientists aren't necessarily sure what's causing that yet, but it's recently realized by citizen scientists, and photos have been taken, which are being used to study it. We also have the stable auroral red arcs, which may be a precursor to Steve, sort of like Steve's dad, maybe. Not sure how you want to weave that in, but the bottom line is that aurora chasers are really pioneering the study of Steve and his friends, and this would not have been possible without aurora chasers directly collaborating with scientists. We have auroral dunes, which are sort of these striated structures in aurora caused by gravity waves propagating upwards, and then the aurora sort of illuminating these waves. They were discovered by citizen scientists in Finland in 2020. These are my favorite, fragmented aurora-like emissions, or FAEs. Relatively unknown. There's only a handful of observations, and they kind of look like little green tic tacs. They're like little blobs that look very similar to the streaks seen underneath Steve's picket fence. So it's possible that these are created by the same physical processes in the ionosphere. And what's really interesting about the picket fence formations is that they actually might not be auroras either. So, not created by precipitation, but rather localized parallel electric fields energizing these particles and creating periodic emissions. So that's some new work that just came out. If you're interested, Claire Gask, I think it's a 2023 paper, and it's not easy being green, a study of Steve's picket fence and parallel electric fields, something like that. But it's all linked in my site, which you'll see at the end, the URL. So these FAEs are cool. I'm studying them with some scientists. We're part of this sort of international team of researchers really working to advance the field of citizen science, Aurora citizen science forward, and facilitate a lot of these collaborations with really directed efforts. So, and just one example of how people can be contributing is I posted on social media like, hey, we're just looking for more observations of these FAEs. We don't really know much about them. And somebody reached out to me with a time lapse. This person, Tom Warner, is I think an electrical engineer by trade, but was just, I think, on some holiday on an expedition on a boat. I'm not sure the context, but he was in very northern areas of Canada, like up near Baffin Island level of latitude, and he just so happened to have a perfectly calibrated aurora time lapse with really accurate GPS and time data. And lo and behold, there were fragments. So that was pretty incredible. We had our first sighting over northern Canada. So it wasn't just a Svalbard phenomenon where these were first discovered. So if you're interested in contributing, there's Aurorasaurus, which is a project I've interned with. They're actually a SciAc project with NASA. So I interned for them in 2020, and really their mission is to make auroras, to make sure people can see the aurora who want to see it. Their site, aurorasource.org, takes in reports. You can submit a positive aurora sighting, and it gets put on a map, and other people can then look at what you've seen and then say, hey, somebody's seeing aurora near me, I'm going to go outside and take a photo. And also submitting your photos, like time lapses or just images of weird things in the sky. Those photos are then made open source and made available for scientists to use. You can also become an ambassador, and there's an application on their website if you want to promote Aurora citizen science and Aurorasaurus in your community. So from the May storm, they had over 5,000 reports, and it's a huge data set that will be very, very valuable to science, because the aurora was so far towards the equator, it was actually outside the field of view of many scientific grade imagers. So in order to study what's going on with the aurora, it really helps to have pictures of it. But if it's outside the field of view of these traditional instruments, well, what are you going to use? You're going to go to the aurora chasers and figure out what they were seeing. So really excited to see what kind of science is done with that data set. There's more citizen science projects with NASA. Here's just a little snapshot. Here, all the different projects that you could explore. And, a lot of them too are not just aurora projects, but there's, eclipse projects. There's the Hamsai group. There's the Sungrazer project. So looking at comets passing through, this is that Soho-Lascaux image, so that coronagraph. You can help figure out what's causing weird waves in the magnetosphere by listening to sonified data. That's the HARP project. There's some really cool stuff. You can also directly collaborate with scientists. So how to make your data more science friendly, recording accurate time and geolocation data with your photos, recording raw files without edits, and submitting your data to online repositories. So I talked about Aurorasaurus. There's also Skywarden, which is sort of the European counterpart, slightly different, but another database which you can submit your photos to, and then scientists can then find those data and then potentially interact with you to get more information, and you could become a co-author on their paper, and lead to other other sort of efforts down the line. I always say if you see something interesting, make a post, right? Don't be quiet about it because it could be the next Steve, right? Maybe it's John or like Billy, right? Who knows? There's all these different names of auroras that are popping up. Seems like every single month or every couple months we're discovering something new, and it's just really cool, right? You have everybody who's now getting into auroras, and even smartphones now can take photos that are almost, everything is science grade, right? Everything is science quality. So yeah, people armed with smartphones now can be making an actual difference, which is just really cool to me. So wrapping it all up, I've talked about a lot here. I've touched on a lot of things, but the bottom line is that we're in solar maximum, and the auroras are just going to keep coming. We're kind of nearing that sort of tipping point where we're going to start declining again. But what's really interesting is that auroral activity peaks slightly after solar maximum. So even though we might be over the hump in terms of solar activity, in terms of sunspot number, for example, we're probably not over the hump in terms of auroral activity. So there's more to come. Excitement for the auroras at an all-time high. It's important to understand the science so that you can weed out the sort of bad apples, all these articles that are clickbaity and confusing people about what the real effects of space weather are. And also now is a great time for people to get involved in citizen science. Every single aurora has a new science opportunity with it, and people taking photos of the aurora, just saying that they've seen it, is valuable for science. So we need more space weather ambassadors, and I hope that all of you are sort of willing to take up the torch and basically tell people about space weather and why it's cool and how the aurora works. We need people who are passionate about the science, educated with the right science, able to bring the science to the general public. I sort of think of groups like the Solar System Ambassadors, or these citizen scientists as like translators between the subject matter experts who really know the complex science and the general public who may be really interested, but they need somebody to break it down to them in a way that they'll understand. So everyone here can be an aurora chaser. Everyone here can be a space weather ambassador. And with that, we have some time for questions, so I'll open it up. But before I do, just want to thank you all for your attention. And if we run out of time, feel free to send me an email. My email's open, and also visit this page on my website for all the links. Thanks.
Hey, Vincent, do you want me to ask you questions from the chat, or did you just want to go through the chat questions?
Oh, there's a lot of stuff. Why don't you ask me the questions?
Yeah, definitely. Okay, so the first one that I see is you mentioned nightly auroras in Alaska. Is that also true during solar minimum?
Yeah, great question. So yes, so the auroral oval is where the aurora is seen at all times, regardless of space weather activity. So you can think of the solar wind as sort of this gentle breeze, and when that gentle breeze hits Earth's magnetosphere, some energy still gets pumped in. So we still see auroras within the auroral ovals. So those auroral ovals are centered around Earth's geomagnetic poles, roughly in a sort of 1 degree latitude width, around 68 degrees geomagnetic latitude. So Fairbanks sits kind of right in that range, and you can see auroras every single night. It's dark and clear here in some sort of capacity, regardless of the solar activity or the space weather activity.
And second part of that question was, in that case, is it from the solar wind rather than the CME?
Yep. So the CME will sort of ride along the solar wind. It's sort of when you actually look at the data, the CME is kind of isolated from the background usually, but the solar wind is always coupling with Earth's magnetic system, Earth's magnetosphere, and some energy is always being directed in. So even when the solar wind's very quiet, even when space weather is very quiet, there's still some aurora there. It never really disappears.
Cool. Let me see. This one says, why is aurora viewing better during the solstice season?
Yeah, so I think maybe they meant the equinox seasons. There's so slightly higher auroral activity over the equinoxes. There's actually not a good scientific consensus as to why this is. So the specific effects are called the Russell-McFerrin and equinoctial effects. So Russell and McFerrin being the last names of two people who sort of found the trend of the data. But essentially what it boils down to is during the equinoxes, the Earth is neither tilted away nor towards the sun. So if you think about the solar wind hitting Earth's magnetosphere, if you kind of draw a diagram, right, you have a BX, a BY, and a BZ, these three components. And when the Earth is neither tilted, nor away nor towards the sun, you have different coupling between these three different magnetic field components and Earth's own magnetic field based on the geometry at those times. So the actual, physics going on, I'm not a true expert in that right now, but there are papers that you can explore by Russell and McFerrin that sort of go over what they think might be causing it. But it's definitely a geometry effect caused by the equinoxes.
Okay, the next question says, have you been involved in any research connected with the 2017 and 2024 eclipses across the US?
Good question. I did bring out a magnetometer, one of these EASY. So EASY IE is, I think it's I can never forget, or I can never remember what the name of the mission is, but it's a mission that's actually flying, which has a citizen science component with all these ground magnetometers that they're pushing out to whoever wants them, essentially. So I got one of these EASY mags, they're called, and it's like a little lunchbox magnetometer. So I actually deployed one during the eclipse, and you can see during an eclipse, because the changes in the ionosphere are so drastic, right? The sun actually creates the ionosphere during the day, and there's layers that are lost at night because there's no photoionization happening. When this eclipse happens, you basically have an area of darkness, right? So these really sharp gradients, which can create magnetic field perturbations in the ground. So I was able to do some cool citizen science with my little EASY Mag lunchbox. It looks like a lunchbox, but there's like a Raspberry Pi and this sort of little low-cost magnetometer inside. And I was able to actually deploy that during the eclipse and get some data. So yeah, I did not see the one in 2017, unfortunately, but I did see the one this year, and that was pretty amazing.
Awesome. Okay, so the next one says, how do these events affect the ozone hole?
Yeah, so I'm not sure about the ozone hole, but there are some types of aurora, specifically pulsating aurora, where the particles are so energetic that they actually penetrate down into a region of the atmosphere called the mesosphere. And there was a mission called the Lost Through Auroral Microburst Pulsations sounding rocket mission, which I helped with in 2022. I spent 3 weeks up in northern Alaska doing sort of groundwork, but they launched a rocket into pulsating aurora to measure the effects of these particles on depleting ozone. So these pulsating aurora particles have such high energies. We're talking about like mega electron volts, that they penetrate down to a deeper layer of our atmosphere where these chemical reactions can deplete ozone. I'm not sure about the amounts and relative to human created ozone depletions, but last I heard, I thought the ozone hole was actually closing due to sort of regulations on certain aerosols, but maybe it's reopened again. I don't think the aurora actually has that measurable of an impact, though, in terms of the overall scheme of things. But on a very small level, it can slightly deplete ozone, these pulsating aurora particles.
Next question. What do you mean by open magnetic field lines?
Yeah, good question. So on the sun, there are magnetic field lines that sort of come out from the surface. If the magnetic field line is open, it just comes out. There's no closing point on the sun surface. There's no loop. It sort of just flows out freely into the solar wind. And if the magnetic field line is closed, you'll have one point on the solar surface, and then it'll sort of loop, and then you'll see it close again on the surface. And let me see if I can go back through my slides. Hopefully this doesn't take too long. And I can show you, yeah, so here's the coronal hole here. So these magnetic field lines, these are just sort of, these aren't, real magnetic field lines. It's just sort of a cartoon, but where you have these bright regions, these are closed magnetic field lines. So basically what happens is these particles become trapped by the closed lines, and they kind of like bounce back and forth and create this glow, which then appears brighter. So like these are over active regions, which are over sunspots, and then open magnetic field lines allow the plasma to escape freely. And that means it's cooler. There's not as much of this sort of trapping behavior. So you can see on the right-hand side here on the sun's limb, this sort of loop. This is an example of a closed magnetic field line. So that's kind of what I mean is you have these sort of magnetic field lines that flow out of the sun and then close back down somewhere else on the solar surface.
Awesome. Okay, next question. Could space weather have any impact on GPS navigation?
Yep, for sure. So actually, during the May storms, I had a lot of friends who are farmers in northern Minnesota and southern Canada, especially Manitoba. I had a lot of friends up there who were telling me that their tractors were just not working and their precision farming equipment was not working because it couldn't find a lock on any GPS. So yeah, global positioning system, really any sort of GPS like network, right? There's GLONASS, there's all these other networks, they can all be affected by space weather. And specifically when there's a lot of particles in the way between the ground and the satellite, it's kind of like, this is a kind of a funny example. I literally just thought of this now. It's like, if you imagine a Connect Four board and like towards the end of the game, you're trying to, have those, sort of pucks fall, they sort of bounce around everywhere, or like those, like at the state fairs, you get those, win an iPad thing and you have to, drop this ball throughout all these little pegs and it sort of does this random walk. Well, imagine that ball is your sort of GNSS signal and it's trying to get through all this stuff in the way. And that stuff is usually protons and electrons caused by solar flares that can ionize the upper regions of the atmosphere, or aurora as well can cause basically larger total electron content in the atmosphere. So the volume integrated number of electrons from the surface of space. So when you get these higher TEC values, you can get GPS scintillation, and it's been measured before. There's a lot of really good papers. One person to look at, and her papers are great, Jade Morton. She's a professor at the University of Colorado. She has some really good information on how GPS can get affected by space weather.
Next question. In places where auroras are visible every night, are they visible all night or just for a limited time?
Can you repeat that? Sorry.
So in places where auroras are visible every night, are they visible like the entire night or just a certain like portion, like a limited time?
Yeah, that's a good question. So yeah, usually auroras really only come out, if it's like a quiet night from 10 p.m. to 4 a.m. And that's just because the auroral oval has to rotate, quote unquote, rotate in. So really it's the Earth rotating underneath the auroral oval. But from the perspective of an observer on the ground, you're seeing the aurora sort of move over your head as the night goes on. So this auroral oval, right? Let's say that you're in Fairbanks, Alaska. This aurora right now, it's sunset is not here yet, quote unquote, here yet. But as you rotate into darkness, that auroral oval is always biased towards midnight. So basically directly sort of on the opposite side of what's called the anti-solar point, where the sun is directly overhead. If you draw a line, let's say this is over here, the aurora is the strongest sort of at midnight. So over the course of the night, the aurora sort of naturally waxes and wanes. You can get little explosions of aurora called substorms. There's a whole substorm cycle. There's the growth, onset, expansion, and recovery phases of substorms, which kind of dictate what patterns in the aurora you see. But yeah, the aurora does not just happen as soon as it's dark. It sort of waxes and grows from around 10 p.m. And this is true with really anywhere in the auroral oval, but specifically does depend on your time zone and also where you are in the world. From 10 p.m. and then you get a substorm usually around 12 to 2 a.m. and then it sort of starts fading away as you get closer to sunrise. So yeah, it's not out all the time in the same way. There's definitely patterns.
This one is actually really interesting. What is the correct or preferred plural of aurora?
So I did some research because I'm always trying to figure this out too, is people interchange aurora and auroras. There's actually no good like recognized or standard semantics. Aurora is also okay, but yeah, it doesn't need to be capitalized either. But yeah, Aurora Borealis is the north, Aurora Australis is the south, northern and southern lights, of course. Sometimes I just say the lights, polar lights. Yeah.
Cool. And I think we have time for just one more question.
Sure.
Can you please repeat which equinox avoids the moon?
Yeah, so that'll depend on the year, right? So the moon, roughly 27 or 28 days in terms of the lunar cycle. So, over the course of years, that'll align or maybe not align on an equinox or a solstice. So you're just going to have to check your moon calendar. I think for September, oh, I don't even know what it is this month when full moon is. You can just check your weather app on your phone and it'll tell you. But um, yeah, it'll really depend on the year. So yeah, just take a look. It should be easily searchable on Google. There are some sites that will give you the moon phases for the next, decades if you really want it. So
Awesome. Thank you so much, Vincent. This
mhm.
was really, really great. Um, and Vincent, if you want to drop your website in the chat
Sure.
for all of the resources that everyone can look up later, that would be great. And then we have our next workshop next week. Kay or I will be sending more information about that and how to register, but it'll be at the same time next week. So we hope to see everyone there. And yeah, thank you so much, Vincent. Again, this was really, really great.
Yeah, thanks for having me. It was fun.
Thank you, everyone.